Hello everyone, my name is Amareshwar Reddy and I am from CSC Department Section A. My topic is about arbitrary complex matrix. Introduction to arbitrary complex matrices. An arbitrary complex matrix is a matrix that has any number of rows and columns and its elements can be complex numbers. These matrices are important in fields like quantum mechanics, signal processing, and mathematics. Studying their properties helps us understand and analyze complex systems and transformations more effectively. Definition of complex matrices. A complex matrix is made up of numbers that have both real and imaginary parts, written as A plus Bi. The size of the matrix depends on how many rows and columns it has. Unlike special types such as Hermitian or unitary matrices, an arbitrary complex matrix can have any values, making it useful in many different fields. Basic properties of complex matrices. Complex matrices can be handled much like regular real matrices. You can add, multiply, and scale them. However, when analyzing them, the conjugate transpose, also called the Hermitian transpose, becomes important. Their eigenvalues and eigenvectors can also be complex numbers, and finding them often needs some special techniques. Matrix operations on complex matrices. Matrix addition and subtraction are done by adding or subtracting matching elements in each position. Matrix multiplication combines rows from the first matrix with columns from the second, multiplying and then adding the results. A complex matrix has an inverse only if it is non-singular, meaning its determinant is not zero. Complex conjugate and transpose. The conjugate of a complex matrix means changing the sign of the imaginary part of each element. The transpose means flipping the matrix so row becomes columns. The conjugate transpose, also called the Hermitian transpose, does both. It takes the conjugate and then transposes the matrix. It is written as AH or A star. Eigenvalues and eigenvectors of complex matrix. Eigenvalues of complex matrices can be complex numbers. They don't always have to be real. The eigenvectors that go with these complex eigenvalues are also complex. To find eigenvalues, we usually solve the characteristic polynomial, which can give complex solutions. In simple words, complex matrices can have both complex eigenvalues and eigenvectors, and we find them by solving a special question made for the matrix. Diagonalization of complex matrices. A complex matrix can be diagonalized if we can write it as PDP inverse, where D is a diagonal matrix and P contains the matrix's eigenvectors. Diagonalization makes calculations like finding matrix powers or exponentials much easier. However, not all complex matrices can be diagonalized, especially if they don't have enough independent eigenvectors or have repeated eigenvalues. These are called defective matrices. In simple words, a complex matrix can be made simple diagonal using its eigenvectors, but only if it behaves nicely and has enough distinct directions eigenvectors. Norms and measures of complex matrices. The Frobenius norm is the most common way to measure the size of a complex matrix. It is found by adding up the squares of all the elements and taking a square root. Another type, the operator or spectral norm, measures how much the matrix can stretch a vector. These norms help check the stability and accuracy of calculations with complex matrices. In simple words, applications in quantum mechanics. Complex matrices are used in quantum mechanics to describe how quantum states behave the change. Unitary matrices show how a quantum state evolves over time without losing information. The eigenvalues of a Hamiltonian matrix represent the possible energy levels that a quantum system can have, like the allowed energies of an atom. In simple words, complex matrices help explain how quantum systems move and what energies they can take. Applications in signal processing. Complex matrices are used to represent signals that have both size, amplitude, and direction phase. In applications like Fourier transforms, they help describe how signal change over time or frequency. Engineers use complex matrices in filtering, modulation, and antenna systems to improve signal quality and signal efficiency. Computational techniques for complex matrix. Here's a simplified explanation of what we have to tell about it. Finding eigenvalues. Special methods like the QR algorithm help compute eigenvalues of a complex matrices. Eigenvalues tell us important properties about the matrix. Solving linear systems. Methods like LU decomposition, breaking a matrix into simpler pieces, are used with complex matrices to solve equations efficiently. Software help. Programs like MATLAB and NUMPY already have built-in tools to handle complex matrix calculations, so we don't have to do all the steps manually. In short, there are smart algorithms and software that make working with complex matrices much easier. Challenges in working with arbitrary complex matrices. When a matrix have complex eigenvalues, calculations can be tricky and small errors can grow, causing instability. Finding the inverse of eigenvalues of large matrices takes a lot of computing power. To get accurate results, you need to choose the right methods and use enough numerical precision. Summary of the key points. Arbitrary complex matrices are just matrices that have complex numbers as their entries without any special rules. We study them using tools like the Hermitian conjugate transpose and by finding their eigenvalues and eigenvectors. They are important because they are used in many areas of science and engineering. Future directions and research. Researchers are working on better ways to handle very big and mostly empty complex matrices. Advances in quantum computing and signal processing are pushing new ideas for using these matrices, making faster and more efficient methods to diagonalize and invert complex matrices is an important goal. Thank you everyone for listening my topic.